another integrals example. This time it's another capacitor example. And it's another one where they've given us current and want us to determine voltage. Again, variables we need to know about: V is voltage, I is current, C is capacitance. So we're giving a piecewise expression for current that varies as a linear function. Between 0 and 2, it's 2t minus 2. Between 2 and 4, it's 2t minus 6. And between 4 and 6, it's 2t minus 10. And for each of those expressions, we need to determine the expression for the voltage, and then we want to sketch the whole thing. So here we go again. We'll work it piecewise. And I'll try to show more steps because this is new. In the past, we've just had constant values here. It's going to be a little bit more complicated to integrate with a linear function there. Okay, so again, without making you watch me do the boring steps, we took this expression, plugged in. We know that our capacitance was 500 millifarads or 0.5 farads. So we plugged that up front. We are going from 0 to t in this case because we're actually starting at 0. Our expression is 2u minus 2. And we are, again, evaluating at 0 because that's where we're starting there. So the coefficient, 0 divided by 0.5 is 2. We do the antiderivative of 2u is u squared, of 2 is 2u. We plug in 0 and t, so we get t squared minus 2t. We plug in the value that v0 is 0. We simplify, we get 4t squared minus 4t for that first part. And we find out that if we plug 2 into the equation, which is our endpoint, we're back at a voltage of 0 at the end of part A. So actually not too bad for part A. Let's move on to part B. So part B, again, 0.5 out front, 2u minus 6 is our expression. We're evaluating at 2, so we have our endpoint at 2, our start point at 2. Antiderivative very similar, u squared minus 6u. But we're evaluating from 2 to t, so when we get inside the expression, we get a t squared, we get a 6t, and then we have to plug in the 2, so we actually get 2 squared and minus 6 times 2. And so what we actually end up with, when everything's simplified, is 2t squared minus 12t plus 6. Okay? So that's part B. One more part. All right. Part C. Again, we have the 0.5 microfarads out front. We're going from 4 to t this time. Our expression is 2u minus 10. And we need to know the voltage at 4, which was 0. Again, the inside looks similar. We evaluate it from 4 to t, so we end up with t squared minus 10t. This part, we end up plugging in 4, so we get negative 24, which becomes positive 48. So our final expression is 2t squared minus 20t plus 48. Okay, so what does that look like in terms of a sketch? Interesting question. Okay, so I know in trying to sketch it, I know at 0 and 2 and 4 and 6 it all ended up back at 0. But I also know that each one of these looks like a parabola. And also each one of these looks like an upward facing parabola because they're all coefficients of positive 2. So basically what I should have are 3 parabolas across here that should each are 0 and back at 0. So what that's actually going to end up looking like is something like this. And one of the ways I can test that, I know it needs to look like a smile. And one of the ways I can test that is if I plug 1 into this equation, which is in between 1 and 2, I would notice that I get 2 minus 4, I get negative 2. Well, that's very helpful because that means that that is, as I would expect, the minimum point of that part of the sketch. So this is, remember here it looks like 2t squared minus 4t. Similarly on the other parts. On the other parts, again, since they have the same lead coefficient, they're going to look the same up front, since they all look like 2t squared. And because they both end at 0, I know that the center point in between each of these things are the focal points. Or not the focal points, but are the vertex. I could use other methods to find the vertex, completing the square, or going back to the derivative and realizing, okay, that this point happens where the derivative equals 0, the derivative is this, so this equals 0 at 3, this equals 0 at 5, that equals 0 at 1. So each of these points here in the middle, 1, 3, and 5, are the vertex. And so we just have this sort of continuing parabola attachment going on. So it's an interesting function that came out with. I don't know what function of a capacitor leads to that, but the main points here are we once again used this function, which relates voltage to current using for a capacitor, and that we did it with a slightly more complicated function. We used linear functions this time instead of ones that just have a constant.